Hello, everybody. Welcome back. Today we're going to be looking at Unit 5.5, which is all about what's called the collision model for how reactions occur. So let's get started. So the collision model, guys, what it describes is how reactions physically occur. And that word collision is key here. Okay, so the key idea is that in order for a reaction to occur, the reactant molecules must actually physically collide with one another. It's actually quite violent. It's not enough for two reactant molecules to simply make contact. They must crash into one another. However, just making a collision isn't actually all that's enough. So just having collisions isn't enough. We're only going to see some of those collisions produce a reaction. And why is that? Because a certain amount of energy is required in that collision, and that energy has a name. It's called the activation energy. And I'm just going to make up a number. All right, let's say a particular reaction has an activation energy of 20 joules. Okay, the particles must collide with one another with 20 joules of energy. So if they collide with one another with 19 joules of energy, that's not going to cut it. The collision has to be 20 joules or greater in order to occur. Okay. Now, if you think about it, how does this tie into the concept of kinetics? If a particular reaction has a high activation energy, meaning in order for this reaction to occur, the collisions must happen with a high amount of energy, that's going to be really difficult to do. So reactions that have high activation energies tend to be slower in terms of their speed, whereas reactions that have lower activation energy values, they will typically happen at a faster rate. Okay. Now, even still, okay, let's think about the requirements for a reaction. Molecules must collide. They must collide with a particular amount of energy, but that's not the only requirement. There's one more requirement. They have to collide at a particular orientation, okay? And what I mean by that is like the angle at which the molecules contact each other, okay? So maybe if my fists here are two reactant molecules, if making contact like this, maybe that angle at which they're making contact isn't going to cut it. But maybe if I rotate this one like 90 degrees and now they make contact, maybe now that will do it. And the whole point behind that is they have to make contact at a particular angle so that, and this is important, so that new bonds can be formed. All right. So let's think about all the different requirements. In order for a reaction to occur and products to be made, reactant molecules, number one, must collide. Number two, must collide with the appropriate amount of energy. And number three, must make contact at the correct molecular orientation so that new bonds can be formed. And if you think about it, guys, with all those requirements, it's almost like a miracle that reactions ever happen in the first place, but obviously they do. Okay, now sometimes you'll be asked questions relating to the collision model that talk about temperature. That's a very common thing to talk about on the AP exam in terms of the collision model. And I want you guys to think about what physically happens to particles when you increase their temperature. Their speeds increase, and not only that, but the particles are moving with a greater amount of kinetic energy. Okay, remember that's essentially what temperature is a measure of, is the average kinetic energy. So this statement should make sense to you. If the speed of a reaction, the reaction rate, is really a factor of how often, what is the nature of these collisions that are happening, raising the temperature, it should make sense to you, should make the reaction rate go up. There's going to be, number one, there's going to be more collisions, just more collisions, period, because the reactants are moving faster, greater speeds. But also, we're going to have more successful collisions because these particles at a higher temperature have a greater amount of kinetic energy. And so we're going to have more collisions with that required activation energy. And it actually goes up exponentially with temperature. And there's something called a Maxwell-Boltzmann distribution curve, which you'll see frequently on the AP exam. So let me help you understand what you're seeing here. The blue curve is representing a reaction taking place at a lower temperature. The red is representing a reaction taking place at a higher temperature. Okay, now, no matter what the temperature is, ladies and gentlemen, a particular reaction's activation energy, that number does not change. Okay, let me say that again. No matter what the temperature is, a particular reaction's activation energy, whatever that value is, that is a set value. Okay, that number does not change excuse me, with temperature. But if you'll notice, if it's sort of like the area under the curve past that dashed line, which is where activation energy is being marked, you'll notice that the red curve has a greater area under the curve past that dashed line, greater area than under the blue curve. That means a greater number of particles at a higher temperature are going to have the amount of energy needed for the reaction to occur. Okay, so when you raise the temperature, okay, you're going to have more collisions. First of all, just a greater number of collisions. And number two, you're going to have more collisions with that required activation energy. Okay, which is going to lead to a faster reaction rate. So I want you to pause the video here and see if you can answer this multiple choice question. All right, so it says, which of the following best helps explain why an increase in temperature increases the rate of a chemical reaction? Before I even read the answer choices, guys, let me say one more time, because this is really important. No matter what you do to the temperature, a reaction has a set value for the activation energy. So I can eliminate answer choices A and B, okay, because both of those say that I'm changing the activation energy, which we're not doing. That's a set value. Answer choice C, at higher temperatures, every collision results in the formation of product. No, not necessarily, because remember, they also have to have the correct molecular orientation. So the answer is D. All right, all that happens when you raise the temperature is you're going to have more collisions and more collisions at a higher energy. So there's going to be more frequent, more fruitful collisions. Okay, here's a free response question, and the first two parts are actually going to be some review from earlier in this unit. And then the last question is going to be something that we've just talked about today. So pause the video, see if you can answer these questions. All right, so the first thing that we are asked to do goes back to the beginning of Unit 5, where it says, determine the order of the reaction with respect to S8, one of our reactants. And we're given this table of data. We're going to use what we called the initial rate method, where we combine one line to another. Remember, guys, if I'm trying to find the order for S8, I want to compare two trials, two lines, where S8's molarity is changing and the other reactant is remaining constant. So that looks to me like comparing trials 1 and 2. Let me show you the math. If you'll recall, this is that initial rate method. The rate law I've written up at the top of the slide, but I don't know what the orders are. I don't know what those exponents are. I've used this math to figure it out, and I can see that S8 is a first order reactant. Okay. The next part says, determine the value of hydroxide, the molarity of hydroxide that was used in trial 3. You'll notice in the data table, there's just a question mark in that place. Considering that the reaction is first order with respect to OH minus. So they're telling us the order. We don't have to figure it out. And if you think about it, guys, if I'm looking at what's happening to OH, I want to compare two trials where OH is changing, but S8 is remaining constant. So I'm going to look at trials 2 and 3. So this is remaining constant. And look at what's happening to the rate. It has been doubled approximately. Guys, the term first order, I mean, what that even means is whatever the molarity is doing, the rate is also doing. So I can see that the rate has been multiplied by 2. First order means that this must also be multiplied by 2. Okay, so my answer here, is that OH minus's molarity must be 0.02 molar. Since they told us it was first order, when the rate doubles, the molarity of OH will also double. Okay. So let me just give you one other example just to make sure you guys have got this. Let's say this number was not 4.19. Let's say it was 6.30. Okay. Well, I can see that has been, from here to here, has been multiplied by 3. But again, they're telling us it's first order. So whatever the rate is doing, the molarity must also be doing. So this would be my answer if it was, if that rate had been multiplied by 3. Okay, so I just wanted to point that out to you. Okay, the last part says, using particle level reasoning, provide 2 explanations that help to account for the fact that the reaction rate is slower in trial 4, and a little bit above it says that the temperature is lower than it was the day before. So essentially, why would a reaction rate be slower if the temperature has gone down? Okay, so at a lower temperature, the speed of the molecules will be less, so there will simply be fewer collisions. Also, the kinetic energy of the particles is lower, so there will be fewer collisions with that required activation energy. So when you take all of that into account, the reaction's going to go slower. All right, so I hope that gives you more of an understanding of how reactions occurring and why some reactions might be faster or slower. It's all down to what is physically happening to them, how often are collisions occurring, what kinds of collisions are occurring. Do they have that right amount of energy? Do they have that right amount of that right orientation? So that's just giving you a little bit of a fuller picture to understand why some reactions have the rates that they do. So I hope that you have learned a little something today, and I look forward to seeing you next time.